This is Jack Jackson. In this video we'll be talking about the exponential rule for doing derivatives of exponential functions. So to get started here, let's think about what the graph of an exponential function would look like. For example, graph y equals 2 to the x power. Well, hopefully you remember what this looks like. Let's kind of go over a few points on this. So 2 to the 0 power is 1, so we got 0, 1. 2 to the first power is 2, so it's 1, 2. 2 to the second power is 4, 2, 4, 3, 8, 4, 16. Every time we go to the right one, we're doubling the height of the curve. So eventually this grows extremely fast. As we go to the left, it's growing slower and slower. So when you go to the left one, we're getting half as big. So it's negative 1, 1 half, negative 2, 1 fourth, negative 3, 1 eighth, negative 4, 1 16th, and so forth. And so we see we have an asymptote of the y equals 0, the x-axis is a horizontal asymptote on the left, no asymptote on the right. It goes up getting higher and higher. Notice the domain is all reals, and all the y's are positive here because it's above the x-axis. Now here's the question, what would the derivative look like? Just based on the shape of the graph, let's see what we can say about the graph of the derivative. Well, let's see. This function is increasing as we go left to right. So that means the derivative is always positive. So the graph of the derivative is above the x-axis, like this one is. What else? This function is concave up everywhere. So that means the derivative is increasing, kind of like this function. Its derivative is increasing. What happens is we go far out to the left. Well, as we go far out to the left, this thing is getting closer and closer to being horizontal, so its slopes are getting closer and closer and closer to 0. So in fact, the derivative has a horizontal asymptote here on the left. In fact, wouldn't the derivative look a lot like the same function? Let's try it out. So let's see if we can fill in the blanks here. I think these are the same questions we asked, so let's run through this again. Notice that the function is always increasing, so the derivative will always be positive, i.e. the graph of the derivative function is always above the x-axis, meaning quadrants 1 and 2. Also notice that the graph of the original function is always concave up, so the second derivative of the function is always positive above the x-axis, and the first derivative is always increasing. Furthermore, notice that as x approaches negative infinity, the graph above, the graph of the original function, levels out approaching a horizontal line. This asymptote has a slope of 0, therefore the limit as x approaches negative infinity of the derivative is 0, and the graph of the derivative has a horizontal asymptote of y equals 0, the x-axis, on the extreme left side of the graph. Actually, the graph of the derivative will look somewhat like the graph of the original function. So now if we use our graphing calculators, like say a TI-84, we could put in the original function in y1, and I'm going to make it a little darker, 2 to the x, and we use math 8, the numerical derivative of the y1 with respect to x, and evaluate it at the next. Or if you have the older operating system, you could put it in like this. The default is 0.001 if you leave out this last number, or you could choose a smaller h, delta x value there if you want. I used a window kind of like this. This is kind of a square window, and so I get a graph like this. And we see the dark graph is our original 2 to the x, and the thinner one, which is over here in the first quadrant, is actually below the graph, is actually the graph of the derivative. Well, technically it's the graph of the symmetric difference quotient, but it's approximately the graph of the derivative. So the derivative should look like that. In fact, here's what the graph of the derivative looks like along with the original function. This is using Graphmatica. And so we see the original function in blue, and the one underneath it is the graph of the derivative. Now, let's try it again. And, well, before we do that, notice that one of these is actually just a vertical stretch of the other. If we take our calculator now and put y3 as y2 divided by y1, look what happens. y3 is a constant. So that means that that if you take y2 divided by y1. That's the derivative divided by the original function. F prime over f is a constant, k. So that says the derivative is a constant times the original function. So it says the derivative of 2 to the x is some constant times 2 to the x, or at least that's what the table is seeming to tell us there. And that constant is about 0.69 something, and which is notice is a little bit less than 1. Now let's repeat the same thing for y equals 3 to the x. So really all you have to do is go back in your graphing calculator and change this 2 to a 3 right here. See what happens. Well, here's what happens. They're even closer to each other. This time the graph of the derivative is just slightly above the original graph. And we can see that because this constant here is just slightly above 1. So it looks like we're still getting the same thing here, that the derivative of 3 to the x is some constant times 3 to the x, but that constant is approximately about 1.1. Okay, now, wouldn't it be so cool if we could pick the right base here? Perhaps it would work out that the derivative would be the same as the original function, with that constant being 1. In that case, the function would be its own derivative. That would be pretty cool. So let's see if we could find such a number. From now, I don't know what this number will be. I'm just going to give it a letter. Let's call it E. Okay, and for the moment we'll call it E. Where do you think E would be? Well, since we graphed this for 2 to the x and the derivative was a little below the original graph, and 3 to the x it was a little above the graph, then probably there's some number between 2 and 3 where it would be, the derivative would be right on the graph of the original function. They would be the same. So probably it's a number between 2 and 3, and since this at 3 it was real close to 1, this should be a number that's probably closer to 3 than 2. Okay, and so we're going to try to find a number where the derivative of e to the x is e to the x. So if that were the case, then e to the x would be the derivative of e to the x. So now the derivative of e to the x would be e to the x plus h minus e to the x over h. Now remember, maybe I'll add one thing in here if it'll. So e to the x plus h is e to the x times e to the h. Property of exponents. But that means both of these have an e to x, and I can factor it out. So I get e to the x times parentheses e to the h minus 1. Now notice we're taking the limit as h goes to 0, but this e to the x doesn't have any h's in it. So it's not affected by that limit. So it can be brought out front of the limit using one of our properties of limits. So the e to the x is a constant as far as the h changing is concerned. Well, that means that this derivative, if this is going to equal e to the x, so e to the x equals e to the x times this limit, divide both sides by e to the x, that means this limit must be 1. Okay, so let's think about that a minute. So what do we want? We want e to be the right number so that this limit is 1. So we could sort of define e that way, or let's keep working with it just a minute. So if h is close to 0, that means this limit is close to 1. Well, the limit is 1, so that means if h is close to 0, this expression without the limit is close to 1. So the e to the h minus 1 over h is approximately 1, close to 1. Multiply both sides by h, and then add 1, and we see the e of the h is very close to 1 plus h, and raise both sides of this to the 1 over h power to cancel the h power out, and we get e is approximately 1 plus h to the 1 over h power as long as h is close to 0. So if we would just take the limit of this as h approaches 0, that would give us the e that we want. And so in fact we're going to use that as the definition of e, and we define e to be the limit as h approaches 0 of 1 plus h to the power of 1 over h. Okay, let's take a look in the graphing calculator what that might be. So actually let me just clear all this out. And let's put this expression in, parentheses 1 plus x to the power 1 over x, like that. And then let's put in some x's. Let's do a table here. Table. And let's do an ask table, where we can put in what we want for the independent variable, and put in something small for x, so 0.0001, and maybe even smaller, 6 zeros and a 1, or 7 zeros and a 1. We could even put in a negative point. 8 zeros and a 1. Okay, and let's see what these, let's take a look at these y values and look at all the digits here. 2.718268, okay, let's look and see what changes. Okay, some of the digits changed right here. 2.718, those first ones didn't change, so we're probably accurate there, maybe a few more now. 2.718281, etc. Even getting closer. Now they're only changing over here. So these are probably good right in here. And this one's even closer still. So these are probably good at least down through here anyway. At least 6 or 7 digits of accuracy. So 2.71828182982. Okay, that's going to be accurate to several different places. Okay, so let me type this in here. So we can use our calculator to approximate this limit as follows. Okay. And so when we do that, we see that we get this number here. Now that may be familiar to you. And of course the E may be suggestive. This is exactly the same E number that we studied in algebra that we use as a base for exponential and natural logarithmic functions. For example, this is the base we used when computing interest compounded continuously. Okay? And this is the standard base for an exponential. It's a constant and it's an irrational number. So it's a number a lot like pi. It's close to 3. Pi is a little bit bigger than 3. E's a little bit less than 3. It's like pi because it's a naturally occurring number. This is a number that we see here. It's the number that you can use as a base so that the derivative of that constant to the x power is the original function. Okay, and it is just like pi is a naturally occurring number. It's the circumference of a circle divided by its diameter. Like pi, it's also an irrational number. You cannot make it into a fraction, and when you make a decimal expansion, that decimal expansion goes on forever without a repeating pattern or a terminating pattern. So now with that as our definition, we can verify that the derivative of e to the x is e to the x, and this will look just like what we used earlier. So the derivative of e to the x is the limit as h approaches 0 of e to the x plus h minus e to the x over h. Rewrite the e to the x plus h as e to the x times e to the h and factor out the e to the x. Bring it out from the limit sign. And now, since we're under the limit as h goes to 0, we can replace this e to the h as 1 plus h to the power 1 over h. That limit is e, and then raising it to the h power. Well, this h and 1 over h cancels, gives you 1 plus h minus 1, which is just h. H over h is 1, limit of that is 1, and sure enough we have e to the x. We sort of engineered it to be that. Now, we can use this to do, along with the this exponential rule for the derivative of e to the x is e to the x, or the derivative of e to the u is e to the u times the derivative of the u, incorporating the chain rule, to find the derivative of any constant base to the x power. So notice this is different than the power rule. The power rule had a variable base and a constant power. The exponential rule has a constant base and a variable power. So we do that, and the first thing we're going to do is we're going to use this property of logarithms and exponentials that says e to the power ln of b is just b. So we could rewrite this b as e to the ln of b. Then we have a power to a power. We can multiply these powers using a property of exponents. So writing it that form, we can see is now e to the u, where we let u be ln of b times x. So now we do the rule we just did along with the chain rule, and we have the derivative of e to the u is e to the u times the derivative of the u. But the u is ln of b times x, which is just a linear function. So the derivative of that is just this coefficient, this constant coefficient, ln of b. Okay, so we put the ln of b in the front, and I rewrite e to the ln of b times x, again using that property of exponents. I rewrite it as e to the ln of b to the x, and then again I rewrite e to the ln of b back as b, and so we get the derivative of b to the x is b to the x times this constant natural log of b. So if you check we get that let's see here. So, for example, if we do the derivative of 2 to the x power, it should be ln of 2 times 2 to the x power, which is approximately what? Well, what is ln of 2? Another thing that e and pi have in common is you have buttons for them on your calculator. And we have a button for ln as well, which is log base e of x. And so the ln of 2 is approximately just that, 0.69, etc. So that is 0.6931471806 times 2 to the x. And if you look back, that is what we got before for that. And then also we can do the same thing for 3 to the x, which we looked at earlier. And it should be ln of 3 times 3 to the x. And let's see what ln of 3 is approximately. Ln of 3, 1.0 something, 1.09, yeah. So we get that, and that is this 1.0986122289 to the limits of that calculator. Okay. So we get that. Which agrees with what we approximated earlier. So let's do another example. What about the derivative of 4e to the 3x. Okay, first we use the constant multiple rule, bring the 4 out front. Then we write the 3x as u, and we have the derivative of e to the u. Derivative of e to the u is e to the u times the du. Derivative of the u. U is 3x, so that derivative is 3. 3 times 4 is 12, so we get 12 e to the 3x. Okay, you can do 20 in just a minute. And then example 21, the derivative of 5 to the x then is just ln of 5 times 5 to the x. So here are a couple exercises for you to do. Go ahead and work those out and come back when you get them done and we'll check them. Press pause now if you need to. Okay, let's go ahead and work this one. So, first step is to bring the 5 out front, like this, and then we're going to let u equal this right here, this power, which means that this is now just going to be u up here. So the derivative of e to the u is e to the u times the derivative of the u. So I can now take the 6x squared, put it back here in place of the u. Now the derivative of the 6x squared, this is going to go away because I'm actually do this derivative now. So this is just 12x to the first power, so we don't have to write that power. And then finally, we can write it. Let's see, the 12, we'll take it and put it with the 5, multiply together, that's 60. Let's move the x over here to the front. And then finally, we'll take the 6x squared and put it in place of the u here. So our final answer for the derivative is there. So that one used constant multiple rule, the e to the power, the exponential rule, and the chain rule, as well as the power rule. Right. So this one's even easier. This is straightforward. It's just ln of 7 times 7 to the x. So pretty easy on that one. Just straight application of the rule. No chain rule to worry about in that one. Next video we'll talk about the product rule. So now think about it. We know how to do derivatives of both exponential and power functions.